Good afternoon. Thank you for coming. I'm Brian Gerkey. I'm CEO of Open Robotics. We're located out in the Bay Area, and we make open source software for robots. And so what I'm going to tell you about today is sort of how we got here, kind of the origin story for the project. I'm guessing most of you, although hopefully you're involved in open source, are probably not involved in robots, perhaps except as a hobby. So I'll tell you a little bit about what the problem is that we need to solve with infrastructure software and robots. Talk about how we got to where we are, and then if you'll indulge me, I just have a few ideas about what has made our project successful in the way that it's been successful. So to roll this back to the beginning, our origin story for starting this open source work in robots has the same origin story that a lot of open source projects do. In our case, I was working in a robotics lab at USC starting in the late 90s, and we were working for a couple of professors there in the upper left, Maya Matarat and Gaurav Sakatme, and then there were a few of us, students and postdocs in the upper right and lower right, who our goal was to do science with robots. We had robots and we needed to do projects with them to develop algorithms, test hypotheses, write papers, and so on. But to make that happen, we needed a lot of infrastructure software to run the robot before we could do the science on top. And so we had robots like that one you see in the lower right. That's a Pioneer robot. It's a venerable robot that's being used in lots of labs, and at the time, that robot came with some closed source software that was made by the vendor. The manufacturer of the robot also sold you a license to its closed source software that you used to interact with all of its peripherals. Now, we were using that, but of course it had problems and it had failings, and eventually we decided that we should just build our own. We're, of course, computer science grad students, we can figure this out. So we wrote what became Player, and eventually the Player Stage project. And Player is a tool that's still used out there now, which basically gives you access to a bunch of device drivers and a handful of algorithms and some developer tools to let you build what we now think of as robot applications. At the time, we were focused on supporting science in the lab. And then to do this work, you also need really good simulation. So Player is the middleware that runs on the robot. Stage is the simulator that lets you simulate those robots when you don't have access to the hardware or you want to run what-if experiments. If you've only got one robot and you want to see what happens when you put 10 in there. So Stage you see pictured in the middle. And then we put it up on this old-fashioned thing which you may or may not have heard of called SourceForge. And because we were rabid grad students, we licensed it all GPL v2. And so we put it up there and we didn't have any idea what was going to happen. In fact, in retrospect, I now know that we did that without officially going through the university channels to request permission to open source it, and that violated their rules. But by the time it became successful, nobody cared to ask about it. So what we found is that we got users and contributors really quickly, and other people in other labs who were using other kinds of robots, kind of like the ones you see on the right there, they were picking up our software and adapting it so that it would run on their robots. And that was an eye-opener for us, because we'd been thinking about this as software that runs this one robot, and now we start to get this sense of abstraction. This idea that robots, just like other computers, you can dump them into equivalence classes, or at least their components. They have lasers, they have cameras, they have motors, and those are all kind of the same at some level, and you can abstract the details away, put that stuff in configuration files, and then use common software to control them. So that became a pretty widely used project. Along the way, some of my colleagues in the lab, Andrew and Nate, started working on a more advanced simulator. And this simulator became called Gazebo, and this is still a system that we develop and maintain actively today. It's a 3D physics-based robot simulator, and it's meant to be a general purpose simulator. So you can describe the kinematics and the dynamics of any robot that you could imagine building. You can festoon it with sensors, you can put it out in a 3D environment, and you can run it around. And that might be because you're trying to test your new robot design. It might be because you're trying to test your robot software. We see increasingly Gazebo used in continuous integration applications. So this is just an example on the right of a compilation of different applications that people have done with Gazebo. Basically anything that you can imagine as a robot. It could be wheeled, it could be legged, it could be any kind of mechanical structure, real or imagined. You can model it and put it in an environment. That includes UAVs as well. And you can simulate it. And our approach to simulation with this tool is to try to make it the best possible stand-in for the physical robot. So the same software that you run against the robot hardware, you can also run it against your simulation. And that lets you develop at your workstation without access to the robot. It also, as I mentioned, lets you run headless simulations to do continuous integration testing. So jumping forward a little bit, we There was, for about a half a dozen years in the Bay Area, there was a funny little robot incubator company called Willow Garage. It was a privately funded R&D company whose goal was just to, as quickly as possible, advance the state of the art in robotics, which was an ambitious mission. And it did that in two ways. One was to build a state-of-the-art research robot platform, which you see on the lower right. That's the PR2, kind of a human-scale mobile manipulation platform. It's on wheels, it's got arms. It's meant to go into labs so that people can do research with it. But we didn't want to ship the robot, just the hardware. We wanted to have great software with it, so we didn't have all these labs this robot was going out to, reinventing the wheel and building all their own infrastructure software. So we took a lot of those lessons we had from the Player project, we rolled them into something that then became ROS, or the Robot Operating System. Despite the name, it's not an operating system. It's actually a set of tools and libraries that run on top of an operating system. So it's an SDK for robot applications, if you will. And I'll say a little more about that in a minute. Along the way, we ended up changing the license. We said, back when, 20 years ago almost, robotics felt like an academic enterprise. And let's just do everything GPL, and we'll make everybody give back, and we'll build a big community like that. At this point, we could see that something was changing, and people were going to start, hopefully, building businesses based on this technology, and we wanted to have more uptake with fewer obligations, so we went with the BSD license, and that's what we've stuck with. I'll say a little bit more about that later. Now, to get a sense of what people do with ROS, sorry, one second. Let's try that one more time. There it goes. So to get an idea about what people would do with ROS, here's a similar compilation from a couple of years ago showing everything you see here is using ROS. And this is one of the ways, in fact, we find out who uses our software, because as an open source project, you don't have to tell us what you're doing. You don't ask us before you download it. We don't track who's downloading it. And if you don't tell us, we'll never know. So every couple of years, we put out a call for videos, and we said we're going to make a montage to tell the community what it is we're doing. And luckily, a lot of people who work with robots like to show off their videos. Especially once you've got it working, you immediately take a video. So we get lots of videos in, and you can see kind of the breadth of applications. And this is everything from crazy humanoid walking robots that are used in research, to delivery robots that are used in production, to increasingly outdoor robots, by which I mean cars, that are on the road doing advanced driver assistance systems and autonomous driving. Because really, all those systems are fundamentally robots in the sense that they connect sensors to actuators with some algorithms in between. So what is ROS? At its core, like I said, it's an SDK. So we take a distributed systems approach to building the system, and that's why the left-hand side with the little arrows and ovals is meant to indicate that it is a distributed system. So we look at solving robotics problems as fundamentally a problem of decomposing the task into smaller pieces, and we follow the old Unix methodology of building small tools, each of which does one thing well, and then being able to hook those things together to build composite systems. So in a ROS-based system, you'll often see on a complex robot dozens of processes running. One of them might be talking to a laser. One of them might be talking to a camera. Those are your sensor drivers at the front end. They're then talking to some intermediate components that are doing filtering, that are doing processing, that are building models. And then that's going through to your decision pipeline, which is saying, okay, here's our goal. Let's make a plan to that goal. Let's develop controls along the way that will apply to the motors, and then that goes out to the motors. And that's in the core and the plumbing. Now, there are lots of great middleware systems out there. In our case, we built our own. We think it's pretty good. There are other ones that you could drop in, and as I'll mention toward the end, we're actually going to get rid of our own bespoke middleware system and adopt an existing middleware standard, because it turns out some other people have worked on that problem as well. Where we really shine with respect to robotics is in the middle two categories. It's in the developer tools, and it's in the capabilities. And by that, I mean, for the developer tools, writing robot software is just as hard as writing all the other software in the world, but you also have interaction with the physical world. You've got this asynchronous environment that is presenting your sensors with noisy and uncertain information. You have to take that in and, within some semblance of real time, decide what to do and then take action. And there's always uncertainty in your action as well. So you've got this complex asynchronous distributed system. You need really good tools to help understand what's going on inside it. So we put a lot of effort into the tools that let you, for example, take all the data from your robot and visualize it in a consistent 3D frame that you can fly around. And that's kind of telling you what the robot is thinking. You can take all the camera images, all the laser scans, all those point clouds, put all that together, then you can see what the robot sees, and then you can try to understand why the robot's doing what it's doing. We also put a lot of effort into data logging and playback, and again into simulation, which is another kind of developer tool. Now on the capability side, it turns out that this idea of abstraction can also be applied to the algorithms, because once you've got a common sense of how a camera image gets formatted before it comes into your perception pipeline, now your perception pipeline can be independent of the details of the hardware. And that means that we can have well understood solutions to common problems, and we can package those up as open source reusable capabilities that people can take off the shelf and put into their product. So we've gotten to that point now. Kind of our flagship example of that is indoor navigation. So if you wanted to put a mobile robot in an environment like the one we're standing in here, you wanted it to roam around, build a map, keep track of where it is, and be able to go from point A to point B without running into stuff, that's off the shelf in ROS. You take that, you put it on your robot, it will work. You may have to customize it for the details of the environment, but you've got the beginnings of an actual product there. And then it's our goal in building all this and putting it out there in open source is to get you as quickly as possible to being able to do your application. Whether that application is doing research in an environment like this, whether it's doing education, or whether it's actually fielding a product. And then it's on you to figure out what's that robot going to usefully do as a side effect of movement within this environment. There's a sub-community within the ROS community called ROS Industrial. This started about 5 years ago. And this came as a surprise to us. So if you think about robotics, there's kind of a new focus on robots now, but robots have been with us since the 50s, depending on exactly how you count it. And they were almost all robot arms. Big, strong, stiff robot arms used almost exclusively in automotive manufacturing, where they have completely dominated that manufacturing process. And they've been really successful. There are something like 1.5 million industrial robots fielded in the world today. Nothing compared to the scale of mobile device adoption, of course, but mobile robots are big CapEx items, and so you buy them only when you need them. But they had a limitation, which is that they had kind of an old-fashioned programming model, which was that you would buy the robot from the vendor supplied you with a control system that had its own embedded, specialized, closed programming language, and then you wrote in that language in that system. And you only had access to whatever it was they put in the controller box that they shipped to you. And that controller box got safety certified by somebody 10 years earlier, and there's no way that it has like a USB 3 port on it so you can plug in your new depth camera. So what these folks are doing is taking that system of an industrial robot that's electrically and mechanically really capable, an industrial controller box that's been safety certified and is rated and is good at what it does, which is real-time control, and then you pack another computer on top and you run Linux, and you run ROS, and you plug in your sensors, and you get access to all these new algorithms, and then you have that second box do supervisory control of the robot. So the robot is still doing what it's meant to be doing, but you take all the reasoning up to a higher level, and then you can generate trajectories and send those down to the robot, tell the robot what to do. This gets you more capabilities. You can solve problems that you couldn't solve before. It also makes your application portable, because one of the crazy things about the industrial robot market is that you have, the old way of doing it is you program in KUKA's language or ABB's language or FANUC's language. They each invented their own programming language for their robots, which means you can make an entire factory of automation with robots. And if you want to go from one vendor's robot to another, you have to throw everything away and rewrite it all from scratch. This is the craziest kind of old-fashioned industrial vendor lock-in you can imagine. So this is still on the way up, but I think this has huge promise for disrupting the way that people build advanced work cells in factories. Now, more recently, as we've been developing ROS, we've adopted the now tried and true model of putting together distributions. So ROS comprises many, many packages. There are thousands of them that do everything from sensor drivers through algorithms and developer tools out to planners and controllers. And it's not convenient to think about all those packages independently and pick the versions that you want of each one. It's much more convenient, like most of us do with a Linux distribution, is to find one that has a code-named release that I like, and I'll take that. And I have some understanding of what pieces go in there, and I have some belief that the people who put it together checked to make sure that all the constituent packages more or less work together. So that's one of the roles that we play at Open Robotics. In addition to developing the core software, we're also making the distribution. So if you like, it would be kind of similar to us doing both the Linux kernel hacking and doing the distribution management like a Canonical or a Debian. So we take all these packages together, we roll them out into the distributions, we give them code names, we give them turtle logos because we like turtles. And every year on May 23rd, which according to Wikipedia at least is World Turtle Day, I don't know if that's really that official, we make a new ROS distribution release. We used to do them every 6 months, but we found that people weren't taking them up that fast anyway, and it was a ton of work for us, so now we do them once a year. And if you find people using ROS, they'll very closely identify with these distros. They'll tell you, I'm running on Indigo, or I'm hoping to upgrade to Lunar soon. In terms of penetration and community size, so one of the things I often get asked is how many people use ROS. And as all of you who are involved in open source projects can attest, that's almost an impossible question to answer. It's just by the very nature of the system, the fact that you can anonymously take the code, there's no registration wall or anything like that, we'll never really know. But like all of you, we also watch our server logs and try to make inferences about our community size. So one of the things we look at is how many people are downloading binary Debian packages from a server that we host, or actually we pay Oregon State University Open Source Lab to host in Oregon. This is packages.ros.org, and this is where our build farm that takes in all the open source ROS packages, converts them into source and then binary debs and shoves them onto this server. That's where all that stuff goes. And so we watch the downloads from there. So literally we're just parsing Apache logs here. And we can see that we're now approaching 250,000 unique IPs per month that are accessing this server. And that's up almost 100% over last year. So on the first point, in terms of scale, a couple of 100,000 active IPs in a month, that is on par with what we see in terms of unique visitors to our other services. And so we think that's about, that's a decent lower bound on our community size. But it is definitely a lower bound because we don't expect everybody to be active every month. And also we're not accounting for mirrors. There are plenty of mirrors of this package server, of our documentation server, and so on. So we think we've got easily hundreds of thousands of users, which within the world of robotics, it's not that big a community. And so we think that we've got a lot of penetration within this community. I'll also mention that the 100% growth year over year, I think is not due to just people downloading these packages. I think it's in part due to robots. And as we've got more companies out there that are selling ROS-based products, I think part of their provisioning procedure is probably fetching packages from us, flashing those onto the robots before shipping them out. In terms of geographic reach, we also track Google Analytics. In this case, we're looking at who's looking at our documentation servers. And if we go back to when we started tracking this about 5 years ago, we saw what at the time we thought of as the kind of state of the hierarchy of influence within the robotics community, with the US on top, Germany a close second, Japan, and then we might get others in Europe, and then we might get others in Asia. And what's happened over the last 5 years when we look at our server logs is we see something that reflects also the new understanding within the robotics community about where all the activity is. We now see China has jumped to number 2, and if I showed you the numbers, you'd see that China is actually within about 1% of the US and probably about to overtake. And in fact, I was in Beijing 6 weeks ago, and somebody pointed out to me that we're almost certainly we're undercounting China because we're only counting those visitors that Google Analytics scores as being from China, and a lot of those folks are exiting China by way of VPNs, and so we're undercounting the actual Chinese visitors, and we're overcounting their VPN exit points, most of which are in the rest of Asia. For example, if I showed you the numbers, Google Analytics actually tells us that 1 in every 1,000 people in Singapore is looking at the ROS documentation, which I find it hard to believe that 1 in 1,000 people in any country is even involved in robotics. So I think they have a lot of VPN exit points there. But still, this kind of shows the rise of China in one sense, but then more broadly, just the importance of Asia within this community, which historically wasn't the case. We've got 6 out of the top 10 users of our software coming from Asia. Now, let's talk about commercial impact. So, like I said, when I got into this in the late 90s, robots were I thought they were way more interesting than like websites and databases. And so I worked on robots. I thought it was purely an academic pursuit. It would never come to anything. But times are changing, and we can look just over the last couple of years and see a couple of significant events to which I like to think we had something to make in terms of a contribution. So on the left-hand side, there's a company called Here that was a division of Nokia, and they were doing mapping with cars. They had cars that were not autonomous. You have a person drive it, but it's basically a Google Street View-like car. It's got cameras, lasers, GPS, IMU, other sensors perhaps. It's taking all that data in as you drive around and then reconstructing that to build maps, street-level photorealistic maps. Now, one day, one of the people I knew at here contacted me and said, hey, I just want to let you know that we've got a fleet of these vehicles, of a couple of hundred of them. They're running on 6 continents, 7 days a week, and gathering data, and it's all running ROS. And I mean, I had no idea, right? This is how you find out people use your project, is they just tell you. And I thought it was great because it's a really cool example of how this is basically half of a robot. It's got all the sensor data coming in, and it's doing some processing on that sensor data, but it's not actually deciding what to do, but that's okay. They still found the tools useful enough that they built the whole system using ROS. And then just 18 months after or a year and a half or a bit more after we wrote that, kind of disclosed that with Nokia, they ended up selling themselves to a German car consortium for $2.5 billion, 2.5 billion euros. On the right-hand side, you can see in a different market, precision agriculture. This is an area that's getting a lot of attention within the robotics community now, especially in countries where, for one reason or another, there is insufficient labor to do food production. So now people are looking at robots as a way to offset that issue, as well as perhaps make the whole system more productive. Blue River is a company in the Bay Area that makes a precision robotic tool that does selective thinning of lettuce plants. So it turns out when you plant lettuce, you overplant them, and then you come back after they've sprouted, and you see which ones look healthy, and you get rid of some of them in order to achieve an optimal spacing. This is a problem I didn't know was out there, but it's very common in agriculture. And the current state of the art to do that, or before these guys came along, to do the thinning process was to send people into the fields with long-handled hose, and they would implement this optimization algorithm while walking down the row, deciding how to space them, and physically removing the ones they wanted to remove. These guys came up with a system where you have a person drive a tractor, it tows behind it an array of these basically little robots. It's got a camera at the front pointing down, and it looks at the plants as it goes over, and at the back of the same device, you have a high concentration fertilizer sprayer. And so now you've got a computer deciding, given some look-ahead buffer, which ones do I want to keep, which ones do I want to get rid of, and you spray the ones you want to get rid of with the high concentrated fertilizer, it kills them. It's a little robot, it's actually a whole array of them, they get towed by a tractor, and last I heard, they were processing something like 10% of all the lettuce grown in this country has those guys' robots involved in it, and that's a ROS-based robot. It's a little vision-guided robot. And they just last month, it was announced that John Deere picked them up for $300 million. So I'm not saying that if we write about your company on our blog that you'll have a huge exit, but it's pretty likely, it seems. Okay, so now I thought I'd talk about just a little bit on lessons learned. And so what are the things that we focused on along the way? So one I hinted at earlier, and you're all already immersed in this and probably have strong opinions one way or the other. I'll just kind of tell you our kind of origin story on this. Like I said earlier, we were doing everything with the GPL, and when we started working on ROS, we explicitly wanted to make this the thing that the industry would build its products on. And we decided we would go with the 3-clause BSD. That was kind of the best guidance at the time, very permissive license, lots of, it's been tested a lot out in the community. More recently, we've switched over to the Apache 2.0, so all new code that we write is Apache 2 licensed. We keep the old code, 3-clause BSD. We just feel like the Apache 2, it has a lot of the same protections and permissions while being a little more modern with respect to things like software patents. One of the other things we did, though, because we didn't want to make this, so I'll say that we, in those sentences, is those of us developing the core of ROS. We're choosing that as our license, but we didn't want to put that on our whole community. So we did what many of you might take to be controversial or overly complicated, is we federated the whole system and said, we don't require a particular license attached to your package. We divide ROS up into packages, but you just have to declare what license it is you're using. And so we have a whole set of tools and infrastructure and websites that present this information that allow you to put a manifest file in your package. You declare what license it is. Our tools will go through and pull that out and allow everybody to find all the packages and understand what licenses they are under. And so that lets you as the author maintain control over what license you're going to attach, Also, because you don't have to give the code to us, we're not going to host it on our server. You're going to put it up in GitHub or Bitbucket or wherever you like to keep code. You get to control how the development work happens on it, when the releases happen, and so on. So we really try to federate the whole developer workflow for these packages as much as possible. Another thing is we spend a lot of effort doing community support online. And I guess I could have mentioned this at the beginning, we're a small organization. Our company is 20 people. And most of us are doing hands-on development all day. We're trying to do new development, adding new features to the platform. We're also doing maintenance, pulling in patches and so on. But we're also doing this kind of community mentoring, community management role. And that is taking care of things like our documentation site. It's our continuous integration server that does pull request testing. It also does all the source and binary deb generation. And we also have our own Q&A forum. We use AskBot, which is an open source alternative to things like Stack Overflow. And I just point this out to say that if you're thinking about starting a new open source community, this is something that you can't possibly pay too much attention to. That the time and effort that you spend interacting with the community, answering questions, fostering newcomers, that's how you build critical mass. And if you don't do that, it's unlikely that you'll ever build a substantial community. I like to think that in our case, we've gotten to the success that we have now in spite of all the technical mistakes we made along the way. There's lots of things in the code that could be a whole lot better. And they are getting better all the time, but even though we got all that stuff, to the extent that we got that stuff wrong, we put a lot of effort into building a community, and that, in the end, is going to be robust against any number of technical choices that we might need to go back and revisit. Now, as part of that community, we sometimes try to figure out who is actually contributing to the code. So this is one of my colleagues, Tilly Foote, went back to our most widely used ROS distribution. This is ROS Indigo that came out a few years ago. And he went back and found, for all of the packages that were released in that ROS distribution, for all of them that are stored on GitHub, what are all the names of the committers who made changes that went into that distribution? And he couldn't fit it on one slide or two, but it took 3. So we have, over 2,800 people made actual code contributions that went into this distribution that we, a team of 20 people, nominally kind of take credit for and take responsibility for. So we couldn't do what we're doing without the efforts of all those people, and they wouldn't do what they're doing, I think, without the efforts that we put in terms of managing that community. And that has everything to do with those online interactions, but also in-person interactions. So we organize our own conference. We call it RossCon. It's the ROS Developers Conference. We've done it every year since 2012. We just finished up our last one in 2017. It happened last month in Vancouver. And that's a group photo that we took at the end of the show. We do it as a 2-day, very technically oriented developers meeting. It's a single track event. I encourage you to come if you have any interest in robots. We'll do another one next year. But what I want to point out here is that, first of all, who knew that you could get 500 people, as we did this year, to spend 2 days talking about open source robot software? I mean, it seems like such an incredibly niche topic that you would never get that many people who are willing to travel and do that. But they do. In fact, they're super passionate about it. And that's one of the goals of a meeting like this, is to get those people together, to have them share their passion with each other. That's how we all get recharged, and we go back to it, and we keep doing this development for our day job and in our spare time, and we take all the really frank feedback that people give us online about our decisions and about our suggested patches, and we kind of remember how good it felt to all hang out together and get to know each other. And I've had tons of those classic interactions you do at meetings even like this one, where you run into somebody and you realize that that's that person you've been working with on the internet for 10 years and you never met that person before. Another strategy that we've really embraced is to bridge to everything. So ROS is not the only thing out there for doing robot software. There are things that came before, including systems like the one that I built when I was at USC called Player that I mentioned earlier. There are other systems that are being developed now as well, and some of them are very popular in specific communities, like the one on the left over there called Moose is very popular with underwater vehicles. It's a distributed communication system, but it's very sparing with the number of bits that it uses, because you're going over acoustic modems in that case. So there are these like narrow systems that get popular in certain areas, And we've never tried to displace those things. We just connect to everything. We say, well, we're not trying to tell you to use ROS. If you've got a thing that works really well, then let's figure out how to just make the most minimal bridge possible to connect your thing to my thing so that you can use the tool that you want. And then eventually maybe it becomes a hybrid system, or maybe you end up adopting ROS wholesale. But that's been a core aspect of our strategy, is not to think about this as any kind of competition. We just want to make connections to everything and reinvent as little as possible. Something else that's helped, I think, a lot has been the access to common hardware. And this is something that has resolved itself in the rest of the IT industry pretty naturally, with the growth of common workstations and laptops and now mobile devices. They all have common components that are all similar enough that you don't really, if everybody has a laptop in the room, we can all do development. But it's a little bit different with robots because you have this physical body which can differ dramatically from one robot to the next. And while you can abstract a lot of it away, it's really, really hard in a lot of cases to directly share like all your high-level code from one robot to another if they're not pretty similar. So one of the things that we worked on at Willow Garage back in the day was the PR2 robot. And what you're seeing on the left there is the photo of the first 11 of those robots that we built at Willow Garage and then gave away at no cost to some of the top research labs all around the world. The idea was, let's get them all to have the same robot with the same software, and all the software is going to be completely open source, and let's see what they do, and let's get them actually sharing their results, which as much as you'd like to think that science is built on sharing of results and reproducibility of experiments, what you'll find is if you ever get very much into the experimental sciences, that's not as true as you'd like it to believe. And the idea of having somebody else in another lab be able to directly reproduce your experiment, maybe refute your results by using your code, that historically has not been very popular. And that's one of the things that we tried and I think made some effective changing with the PR2 program. More recently and at a lower size are the TurtleBots that you see on the right. So the PR2 is a great robot. You can still buy them. They cost about $400,000 US. So not everybody can have one, probably. And so for those of you who can't, we decided that we should have something that still runs ROS and is a first-class supported platform, but it's going to be a little lower cost. So we came up with a TurtleBot. The top two are the TurtleBots 1 on the left and the 2 on the right. They're based on repurposed vacuum cleaner bases. The one on the left is the iRobot Create, which you might have played with when it first came out, and it's just come back as well. And then, so those run about $2,000. And the idea is that this is a mobile robot. It's got a depth sensor on it. It can do all that indoor navigation stuff that I mentioned earlier. It runs ROS as a first-class supported platform, but it's $2,000, which means you might not buy it for a hobby project, but you might get your lab to buy it for research purposes, or you might get a teacher to buy a handful of them for educational purposes. More recently, we worked with Robotics, which is a robot company in South Korea, to build the TurtleBot 3, which are on the bottom there. The one on the left is called a burger. The one on the right is called the waffle. And they are much smaller. So the burger I could hold between my two hands like this, and then the waffle is about this big. And those run about $500 and about $1,500 each, something like that. So we're trying to push that price down to make this whole thing more accessible, with the theme being that we make these systems as open as possible. So with the TurtleBot 3s, for example, not only do you get a single board ARM-based computer of some kind that runs Linux and runs ROS and has pretty much all open source software on it, but you also get an ARM Cortex-M microcontroller-based motor controller board that is also totally open. So you can reprogram all the motor controller firmware if you think you know how to do servo control better than the people who built the servos. So the idea is we make all that stuff open all the way down. We give it a platform that allows you to actually share your applications across robots, and then from that we hope to see growth in the space of these shared applications. Something else that we did is we decided to take neutrality very seriously. So as I said, when we started the ROS project, we were at a company called Willow Garage, which was ostensibly a for-profit entity that just happened to be spending almost all of its resources building and giving away robot hardware and robot software. And that's really cool. That's really great. And a lot of people you tell that to, they say, wow, that's awesome. How do I get more of that? But then sometimes the more serious people in established companies say, wait a minute, that sounds like a free lunch. I'm sure that eventually you're going to compete with me, or if you keep doing this, you're just going to go out of business, or something else, right? They were asking themselves, why is it that you're doing this? I kind of don't understand the motivation. And there were some folks out there who did not adopt ROS exactly because they felt like there wasn't a neutral steward to the project. And so that's what we did in creating Open Robotics, which is an umbrella brand that encompasses the Open Source Robotics Foundation, which is a 501c3 public charity, as well as the Open Source Robotics Corporation, which is a subsidiary body, which is a taxable entity, and that's the entity through which we do work with industry. So if you're familiar with the way that Mozilla ended up organized, we're organized in a fundamentally similar way. But the key thing there was, even more than the nonprofit versus profit, was to have a company that was dedicated to stewarding the project. And that's what we did in creating Open Robotics. And that's how we can go out and tell the world, this is what we do. We make open source software for robots, and we want all of you to use it. I guess I don't have to tell this group this, but I truly believe that openness accelerates whole industries. I'm showing you here kind of a highlight of some of the products and services that are out in the world today that you can either buy or get prototypes of, or at least experience in some way, that are using ROS. And that's everything from, on the upper left, you've got agricultural applications coming down through self-driving vehicles, delivery applications of various kinds. On the right side, you've got the whole logistics space. There's a whole new generation of robots that are roaming around factories and warehouses, moving stuff from one point to another. Now they don't need lines, they don't need wires buried in the concrete or fiducials on the walls. They can navigate around just fine by themselves. A lot of those are running ROS. I would guess it's a majority of the new entrants to the market, but that's sort of hard to measure. You've also got some security applications as well as some emerging consumer products. People are still trying to figure out what a home robot should do. Everybody seems to want a home robot, or they want to build a home robot, but we're still trying to figure out, once it's in your home, what's it gonna do for you if it's not, vacuuming. So let's see, what is next? We are hard at work on ROS 2. So the details of that are beyond the scope of this discussion to get into like what we're changing, but fundamentally we want to cover some use cases that we didn't really cover the first go round. Now we've got almost 10 years of experience to look back and see what are the things we would have done differently. And now we're going after some smaller systems, some bigger distributed systems, some things like real-time control in a more serious way, as well as just pushing for easier and better product development. As I've argued, we have plenty of companies out there now that are shipping products based on ROS, but there are also some that are not yet, and we're trying to close that gap as much as we can. We're also hard at work on the next big version of Gazebo, and there we're focused on doing cloud-hosted simulation. This is one of those tasks that lends itself really naturally to being put in the cloud. It's a heavy compute kind of application. It tends to be platform dependent. It's the kind of thing that it works best if you run it on a Linux system with an NVIDIA GPU and a correctly configured set of drivers. And that's just one of those things that you don't always have right in front of you. So it's much easier if you can do that up in the cloud. And we've done a lot of things using Gazebo for cloud-hosted simulation, actually for a bunch of government R&D projects in various domains, and now we're looking at how to make that just more broadly accessible so people can use it in everything from continuous integration to education. If you want to have all of your students suddenly be programming a very realistically simulated robot, we can just do that all in the cloud and they'll have some web interface to it. And then finally, I'll mention kind of the next big thing. I don't know if you've heard about this thing called autonomous cars. It is, let's see, and there we go, okay. So, everybody and their brother has an autonomous car startup. You should all go start one right now, and you can sell it next week. But seriously, there is a huge amount of activity in autonomous cars and advanced driver assistance systems, and increasingly they're using ROS, which was surprising to us at first because we built ROS to run on research robots in labs, but then when you think about it, those cars are also just a kind of a robot that happens to be outside. So 2 examples I'm showing you here are of open source self-driving car software stacks that are completely based on ROS. So this is taking those tools that I described earlier, then layering more capabilities on top, and then releasing the result as open source. So on the right side is one called AutoWare. It's from a company in Japan called Tier 4. And that's a system that will more or less do what they call level 3 autonomy out of the box with a correctly outfitted car. It's not a product. It's not safety certified. You should totally not rely on it. But it is the thing that will get you going toward your self-driving car product or service. Similarly, about the same time, on the left-hand side, Baidu, which a company you probably know of, released their Apollo self-driving car stack. This is also completely based on ROS. In fact, they made a ton of really interesting core changes to ROS, which we're now talking with them about how to upstream. And they've released all of that open source. So this is, Apollo has had a large team, or Baidu has had a large team working on Apollo for the last several years, and they're now staging the release of Apollo with new features in it, with the hope of getting an entire industry taking this basic self-driving car functionality as something off the shelf, and then customizing it, testing it, certifying it, and rolling it out into products. And again, it's all based on ROS. So I'll just leave you with one last little teaser here. This is something this is an industry we definitely want to support, is using ROS in serious ways in cars. And also we want to do good simulation of cars. And Gazebo, as you might have seen from those earlier videos, one of the big knocks on Gazebo is we were at a conference one time, and we had a demo where we had Gazebo outputting to an Oculus headset, and so you could put it on, and then you could experience this fly-through experience with this quad rotor. And we showed it to like a 9-year-old, and he did it for a while and then took it off, and he said, that's pretty cool, but your graphics suck. And I was like, but the physics are really carefully simulated. And that's the trade-off we have, right? Is we come from a robotics community where we want to get the physics right, we want to get the sensor models right. We're not, game makers or movie makers, so we haven't historically focused a lot on making everything look shiny and photorealistic. So this is something that some of my colleagues did actually just over the course of last week. You can see some of the laser data being simulated there. So this is a rough model of a Toyota Prius running through a cityscape that we built. And here we're basically just taking a bunch of the off-the-shelf game techniques and throwing them in there to bling the whole thing up. Now, in part, that's just to make it look cooler, and you should not underestimate the importance of that, because making it look cooler will totally, influence the decisions of people who are going to use it or not. But there's a serious use here, which is that we know these cars are going to be using cameras as a key part of their decision-making pipeline. And to believe that that system is going to work well, we need to be able to test those systems with realistic sensor input. And that means that we need to have, and because we know we're never going to test these cars in the physical world as much as we need simulations that will produce realistic sensor data, including camera data, to feed into these systems to both help train them and to test them as part of the certification process, as well as many other aspects of the whole development pipeline. So this is an area where we're starting to put a lot of resources with Gazebo, is into getting it to the point where it can do photorealistic rendering so that we can support all these new applications. So with that, I will stop and just say thank you.